Welcome, my dear student. Myself, Sjctnc-Differential, Assistant Professor, Department of Mathematics, St. Joseph College of Arts and Science, Autonomous, Kadapa. This is the video for differential geometry. It is an Unit 2 Part 3 video. Part 1 video, we discussed about tangent surfaces and fundamental existence theorem. And part 2 video, we discussed about the helix, cylindrical helix, and problems based on the helix. In this video, we are going to see the metric surfaces and some topics helix and problem based on metric surfaces. So now we are going to see the metric surface, the local intrinsic properties of a surface. First, we are going to see the definition of surface. A surface is the locus of a point P which satisfies some restriction, that is, the coordinates x, y, z of P satisfies a relation of the form f of x, y, z equal to 0. This is called the implicit or constant equation of the surface. Explicit form. A surface is defined as the locus of a point whose Cartesian coordinate x, y, z are function of two independent parameters u, v, say x equal to f of u, v, y equal to g of u, v, and z equal to h of u, v are called the parametric or freedom equation of a surface, and this is called the explicit form. That is, we are choosing more than one independent parameter, we will call it as the explicit form. And vector form. A surface is defined as the locus of a point whose position vector or vector can be expressed as a function of two independent parameters, that is r vector equal to r of u, v represent a surface. We know what is a vector. Vector is a magnitude as well as direction of any object. And already seen the first unit and first video onwards, we are how to write a vector. That is, how to write a vector. First of all, r vector equal to r of. Here we are choosing two independent parameters, so therefore we write r vector equal to r vector of u, v. The next one is the Monk's form of the surface. If the surface can be represented in the form z equal to f of x, y, then this representation is called the Monk's form of the surface. So any parameter z equal to f of x, y, then we call it as the Monk's form of the surface. So now we are going to derive some problems. Prove that the parametric equation of a surface not unique. So any parametric equation of any surface is not unique. So it is proved by some example point. So now we consider the two parametric representation. Let us choose some equation. X equal to u, y equal to v, and z equal to u square minus v square. It is a one parametric equation of second degree. Similarly, x equal to u plus v, y equal to u minus v, and z equal to 4u. It is another one parametric representation. So, the elimination of u and v in the first case, we may write x square minus y square equal to u square minus v square. Since x square minus y square equal to z. The elimination of u and v in the second case, we may write x square minus y square equal to u plus v the whole square minus u minus v the whole square. Therefore, we write 4uv. It is x square minus y square equal to z. In both the case, we can get the same Cartesian equation. Thus, the parametric equations of a surface are not unique. The next problem, prove that sometimes the constraint equation of a surface represent more than the parametric equation. Consider the parametric equation x equal to u cos hv, y equal to u sin hv, and z equal to u square. With the parametric equation of the surface where u and v take all real values. Now we elimination of u and v, we will get the value x square minus y square equal to u square cos h square u minus u square sin h square u. So that is equal to u square, since we know cos h square v minus sin h square v value is 1. So which gives x square minus y square equal to z, which is the constraint equation, represents the whole hyperboloid, but the parametric equation represents only the part of the surface y is greater than or equal to 0. Since u takes only real value, sometimes the constraint equation of the surface represents more than the parametric equations. So next one is the class of surfaces. The next definition is class of surface. Already we seen the first unit, second and third video of class M function. What is a class M function? It is the mth derivative exists at the any point of the surfaces. So now we are going to define a class of the surface. Let the equation of the surface in parametric form, we know x equal to f of u comma v, and y equal to g of u comma v, and z equal to h of u comma v. So the surface is said to be class R, means if f, g, h are single valued and continuous, first of all. Second, f, g, h possess the partial derivative of orthogonal. Here we are using small f only, that is not capital F. And for by mistake we are typing capital F. It is a small f only. F, g, h possess partial derivative of orthogonal, and it is single valued and the continuous function. So now we use some notations about that. If r vector equal to r of u comma v with vector point equations, we will use hereafter the differentiation with respect to u means we are using r1 vector. Differentiation with respect to v means we are using r2 vector. However, we are using the differentiation with respect to s means dash, and differentiation with respect to u means dot. Like that, hereafter we will follow some notation. Any r vector can be differentiated with respect to u, we will use r1 vector. Differentiation with respect to v, we will use r2 vector. Next definition. Regular or ordinary point. Let the position vector r vector of a point P on a surface be given by r vector equal to x comma y comma z, and we may write r vector equal to x of u comma v, y of u comma v, and z of u comma v. Then now we differentiate r1 equal to dou r by dou u, that is dou x by dou u, dou y by dou u, dou z by dou u, that is x square, y square, and z square value. Similarly, r2 equal to dou r by dou u, which implies that dou x by dou v, dou y by dou v, and dou z by dou u, and which is also x square, y square, and z square. That is, the point P is called a regular point or ordinary point if r1 vector cross r2 vector is not equal to 0. That is, the rank of the matrix for this expression is 2. That is, simply we say that the point is regular point or ordinary point, means if r1 vector plus r2 vector is not equal to 0. Otherwise, the rank of the coefficient matrix is 2. Next definition is singularity. The point P is called singular if r1 vector plus r2 vector equal to 0. Singularity is divided into two types. One is essential singularity, another one is the artificial singularity. These are essential singularity. First we are going to see essential singularity. These are the singularities due to the nature or geometrical feature of the surface, and these are independent of the choice of the parametric representation. Example, vertex of the scope is essential singularity. Artificial singularity. This singularity arises from the choice of the parametric representation. So let R vector be the position vector of a point in a plane referred with respect to the polar coordinates r, theta. So now possibly we choose R vector equal to R cos v, R sin v 0, and you may write that one is R vector equal to u cos v, u sin v, 0. So now we differentiate with respect to u, r1 equal to dou r by dou u. So that is equal to cos v, sin v, 0, and r2 equal to dou r by dou v, that is minus u sin v, u cos v, 0. So now we are going to find r vector plus r2 vector, and this is equal to some rk. So this is equal to 0 if the pole is 0. That is, if r equal to 0 means r equal to 0 is an artificial singularity.